Okay, ladies and gents, we are in the middle of finding out how on earth the theory of plate tectonics was discovered. If you have managed to get your hands on a module booklet, we're on pages 9 and 10. If you haven't, don't panic. Find the digital version in the folder I sent you. Actually, I also sent you a direct link to the Word document. And we're on 2 pages where the heading says plate tectonics, then there's a map, and then there's a table. If you're there, you're in the right place. The first video gets us up to this gentleman, Alfred Wegener, who is really very important. I will resist the urge to play the song to you again, but he's so important that a song was written about him. We are starting this video with the Mid-Atlantic Ridge, M-A-R, Mid-Atlantic Ridge. So, this is the Mid-Atlantic Ridge. It's under the sea, so you're unlikely to ever have seen it. And it is kind of exactly what it suggests. It's in the middle of the Atlantic Ocean, and it's a ridge, so it's basically a mountain chain under the sea. Okay, why is it important? Well, in the Second World War, they used submarines. So I'm not a history teacher, very clearly I am not a history teacher. My historical knowledge is pretty shocking. But in World War II, we started to use submarines, and submarines navigate with a system called sonar. All right, so that's as much as us geographers really need to know. You may know a lot more about sonar from other subjects. But anyway, that's how submarines navigate around. And the sonar of the submarines allowed them to discover this mountain range in the middle of the Atlantic, which, let's be honest, is quite unexpected and quite surprising. And it was a bit of a turning point. And then, obviously, once the war was over, they started doing more research into this Mid-Atlantic Ridge and discovered that actually there were these lines of mountains under quite a number of the world's oceans. So, closer inspection revealed that, so we're in the 1961 row now, that they were lines of volcanoes, or as it says there, linear line volcanic chains. So lines of volcanoes under the sea. What is important about this discovery, ladies and gents, is because what happens when you have a volcanic eruption, of course, is you have the eruption of lava, so molten rock. If you think of, your stereotypical video of a volcanic eruption, you've got this orange and red stuff coming out of the top. You'll know a lot more about that in a few weeks' time. And what that lava is semi-molten rock. And as it cools, it will become solid rock. Okay, so they discovered that there was lava coming out of these volcanoes, which created new sea floor. And then it's kind of like a conveyor belt. Because those volcanoes would be more or less continually erupting, as that sea floor moved away from the line of volcanoes, it kept getting replaced by more and more lava. Now, their immediate thought, and don't judge them too harshly because actually it's quite sensible, their immediate thought was, well, the world must be getting bigger. Because if we've got these lines of volcanoes all over the world and they're spewing out this lava, which is creating new seafloor, the world's getting bigger all the time. And then they did a few calculations and discovered that absolutely no, the Earth is not getting bigger. So what that then tells you is, if you're getting new land created somewhere on planet Earth, it is being destroyed. And this is seriously important because Alfred Wegener, he was called a crazy man in his lifetime because people said, there's nothing that can move continents. What on earth have you found that's powerful enough to move Africa? That kind of thing. Well, this is the conveyor belt that makes it possible. And it's all thanks in a way, I know it sounds really weird to thank a war, but all thanks to World War II and the use of sonar. So we discover the Mid-Atlantic Ridge, this line of volcanoes. We discover that new seafloor is being created. The automatic thought is, oh, well, the world's getting bigger. Scientific calculations proved that that is not true at all. And then they realised that if you had, and I'm going to use the terminology that some of you will be familiar with here, if you have constructive margins where land is being created, you must have destructive margins where land gets destroyed. And that is the conveyor belt that makes continental drift, plate movement happen. But it wasn't discovered until Alfred Wegener was dead. Now, here's the bit you're not going to like very much. And if it completely blows your mind and you just think, no, I'm never going to get my head around this, it is not the end of the world, all right? Really, not the end of the world at all. But I'm going to have a go at explaining what it says in the 1963 row about magnetic reversal stripes. This is also known as Paleomagnetism, and there is some information on page 10, but also there's a bullet point on page 12 that says Paleomagnetism, and there is a diagram on page 13. So there's a few bits, and I've got some additional information in this video. But can I just repeat, if you really, really hate this, just leave it, okay? It's a show-off opportunity, but it's not the end of the world. Okay, paleo means past. Paleomagnetism means the past magnetic field of the Earth. Right. Think about a compass, and I don't mean a compass that you use to draw a circle with, I mean a compass that you use to navigate. You might have one on your phone, you might have an old-fashioned compass at home, and it might actually help you to dig one of those out. Get your phone app and open the compass app, or actually find a compass in your house. I think having a look at it will actually help you. So what you'll find is that as you move the phone or the compass around, there will be some kind of arrow or red dot or something that will point to the magnetic North Pole. So you can move the phone or you can move the compass as much as you want to, but the red arrow, the magnetic bit, will always point to the magnetic North Pole. Okay? So here's the thing that might blow your mind. The magnetic North Pole is not always at the North Pole. This map proves to you that it wanders around. Okay, so you can see it's wandered quite a lot, but notice that predominantly speaking, if you were in the UK and you were trying to navigate your way around Dartmoor or somewhere, you're always going to be pointing north, so it doesn't really matter. Sometimes in Earth's history, the magnetic North Pole has been at the South Pole. It's called magnetic reversal. It's very weird. We are geographers. We don't have to fully understand this. But if you're going to go with me on this, remember, you don't have to. If you're going to come with me on this, you just have to accept that the magnetic North Pole moves around and sometimes it actually ends up at the South Pole. Right, now, let's go back to the Mid-Atlantic Ridge and our line of volcanoes. This is a diagram trying to represent that. The significance of that line of volcanoes is that the rock is partially melted. All right, there's movement, it's semi-liquid. And that means that any magnetic particles in that magma can move because the rock is molten. And what's going to happen is any magnetic particles in that magma, they're going to behave just like the red arrow or the red dot on your compass. They are going to move so that they are pointing at the magnetic North Pole. All right? But as that sea floor moves away from the Mid-Atlantic Ridge, it's going to cool down. And then you're going to have a solid rock. In that solid rock, the magnetic particles are stuck. They cannot move anymore. So what you have is a record of which direction the magnetic particles were facing. Okay, if I've blown your mind, I am really sorry, just you can stop. If you think you're prepared to come a bit further, lovely. Now, what all of the diagrams I've ever seen give you the impression of is that the ocean floor is stripy, and I hate to disappoint you, but it actually isn't stripy. What they're trying to represent is that here, in the white stripe, all of the magnetic particles are going to be pointing north, because it's a period of normal magnetism when all of the particles are going to be pointing towards the magnetic North Pole at the North Pole. But if we have a period of reverse magnetism where the magnetic North Pole is at the South Pole, I know that's weird. They're using the colour change to just give you the idea that something's different. And what is actually different is that the magnetic particles will be facing the opposite direction. And then we go back to normal and the magnetic particles will be facing. So the stripes are not actually stripes. They are just there to tell you that something has changed. Okay, now here I've included a little, oh, it's because I'm on a Mac. It should work for you, unless of course you're on a Mac as well, sorry. That little hyperlink is to an animation that you can actually play around with this that might help you. But if you're using anything to do with Apple, yeah, it probably won't work. Sorry, I'd forgotten that. Here, quite embarrassingly, is my brilliant diagram to represent this. Now, I've deliberately left you space on page 13 for this diagram because I do draw it in class. I'm sure you're gutted not to have missed this happening in real life. Not. Some people find this useful. What I'm trying to represent here is that the ocean floor is not actually different colours. It's not like a zebra. It doesn't have stripes on it. What is different is that when the magnetic North Pole is at the North Pole, your magnetic particles will all point that way. And when the magnetic North Pole is at the South Pole, your magnetic particles are facing the opposite direction. So that just helps some people understand it's nothing to do with the colour change. They just use the colour to represent that something's different. Because let's be honest, drawing all of that is a bit of a faff, and you can make quite a bad job of it, as I've proved fairly spectacularly. Now, here's the $64,000 question. Why do I care? Why do I need to know about paleomagnetism? And the honest answer is, it's not crucial. It's a show-off opportunity. But what paleomagnetism absolutely, conclusively does is it proves the idea that new sea floor is created at these ocean ridges, and then it moves away, because there is no possible way that this bit of seafloor was created at the same time as this bit of seafloor. It's fundamentally impossible. It's just, you know, like if you were trying to prove something in science and you had 3 bits of evidence as opposed to 1 bit of evidence, it's much more convincing. So all that paleomagnetism does is it's like, look, not only do the rocks get older, but the magnetism is different, plus we've got the fossils, plus we've got the geology, we can prove our point. So that's why it's not crucial, because you can talk about the other bits of evidence if you need to instead. That brings us to the grand finale. J. Tuzo Wilson. What a brilliant name. J. Tuzo Wilson is the gentleman who gets the credit for the theory of plate tectonics. So the theory of plate tectonics, as we know, is quite young. It came around in 1965, which I know seems like ages ago to you guys, but it's not really that long ago. Really, all J. Tuzo Wilson does is he reinterprets what Alfred Wegener came up with. But remember that between Alfred Wegener and J. Tuzo Wilson, we have got completely undeniable evidence that there is something powerful enough to move the continents, and that's why he wasn't taken seriously and he was. So that's why I've tried to use a table, because the order of the events is quite important for you to understand. Now, I'm generally a little bit harsh on J. Tuzo Wilson because I'm an Alfred Wegener kind of a fan, but I should just point out that J. Tuzo Wilson does add something. He adds the Wilson cycle. Now, you've got some diagrams on page 14, or if you've got the digital version, it's a cyclical diagram. So you've got 1, 2, 3, 4, 5, 6 diagrams joined by some arrows. That's the Wilson cycle diagram. And this is a video of it. Okay, so that's stage 1. You've got a continent. So remember, we started off with Pangaea, where all of the continents were joined together. How did they split apart? What happened? Well, this is what happened. You get an upwelling of magma underneath that big continent, and it begins to split the continent apart, and you get this valley and you get some volcanoes. This is happening in Africa right now. Africa is being ripped apart by this process. It's called a rift valley, and we'll know lots more about it in the next week or so. This is clearly much more sped up. Now, you have exactly what's happening between South America and Africa here. This is a mid-ocean ridge. Here is South America, here is Africa, and they are moving away from each other because, of course, our line of volcanoes is producing new crust all the time. Okay. But, now here's the weird bit. You've got to remember that this is happening over millions of years, millions and millions of years. Over millions of years, the direction of plate movement could well change. Now look, the continents are moving back towards each other, and this is what you probably call a destructive margin. It's called a destructive margin because crust is now being destroyed. It's the same purpose of using that word as it was in coasts. Constructive waves create beaches, destructive waves destroy them. Well, constructive margins create land and destructive margins destroy it. So you can see here, you've got your crust being destroyed. And look, our two lumps of continent are moving back towards each other again, which is kind of weird. Got some volcanoes here, and look what's going to happen. The two bits of continent are going to crash into each other. Now, a modern day example of this would be India crashing into Asia. And as that crash happens, look, ooh, you get a mountain range created, a bit like the Himalayas. And hey presto, the two bits of continent are joined back together. So what J. Tuzo Wilson brings to the party is the Wilson cycle, which explains the kind of the separation of Pangaea, the crashing of India into Asia in a lot more detail than, to be fair, Alfred Wegener did. But as I said, I'm fairly obviously biased to Alfred Wegener. So that is plate tectonic theory, how we know about it, etc. You may need to do a bit of pausing, rewinding, going back over, which is absolutely fine. But can I just remind you that from this point onwards, Nick is going to do weekly question and answer sessions for tectonics. So by all means, send me questions which I can forward on to him, or send Nick questions directly. But by all means, ask questions about this stuff, because some of it is quite likely to confuse you. Well done, ladies and gents. I'll see you next time for some structure of the Earth.